In this video, we're going to write or graph linear functions and use them to model situations from Unit 9b. Assume that the following situation can be modeled by a linear function. Write an equation for the linear function and use it to answer the given question. Be sure you clearly identify the independent and dependent variables. Then briefly discuss whether a linear model is reasonable for the situation described. The price of a particular model car is $21,000 today and rises with time. So that means time is my independent variable and price is my dependent variable here. And there's my initial, there's my slope right there. And this is the original 0.02100. How much will the new car cost in 3.2 years? And we want to find the price there. So select the correct choice below. The independent variable is time in years, and the dependent variable is the price, P, in dollars. So let's use, like they did here, T and P. That's good. We don't always have to use X and Y. So the linear function is P of T is equal to 900 T plus 2100, 21,000, excuse me. And the price of the car after 3.2 years is going to be 900 times 3.2, 0.18, 180, 0.0027, that's 2,700, 0.082. That is 2,880 plus the original 21,000. So 0.00021 is 8. So we get $23,880 for that car in 3.2 years. Is the linear model reasonable for this situation? The linear model is most likely not reasonable because it is unlikely that the price of a new car of the same model will increase at a constant rate. Let's assume the following situation can be modeled by a linear function and write an equation for the linear function and use it to answer the given questions. Be sure you clearly identify the independent and dependent variables. Is the linear model reasonable for the situation described? And assume time can be allocated in fractions of a minute. So you can rent time on computers at the local copy center for a $6 setup charge. Here's your fixed cost, and an additional $3.50 for every 10 minutes. So if it's $3, let me just write it this way. If it's $3.50 for 10 minutes, that's 35 cents a minute. There we go. That way I don't have to change it into 10-minute increments for my variable. We'll just leave it as increments of minutes or fractions of a minute. And that is my linear function. So the independent variable is going to be time and the dependent variable is going to be cost, which they're going to call r. Okay, and the linear function that models the situation is r equals 0.35t plus 6. And how many minutes can be rented for $24? So 0.35t plus 6 is equal to 24. So 0.35t is equal to 18. T is going to be 18 over 0.35. Pull out your calculator. And we get 51 with some change left over. So we're going to say 51 minutes, 51 whole minutes, because they say round to the nearest minute is needed. And a linear model is reasonable in this situation because the rate, the cost per minute here is constant. Suppose your dog weighed 3.4 pounds at birth and weighed 14.3 pounds 1 year later, based off of these two data points. So 0, 14, so 0, 3.4, and 1, 14.3. That gives us a slope of 14.3 minus 3.4 is 10.9 over 1 is 10.9. Based off of these two data points, find a linear function that describes how much weight varies with age. Use this function to predict your dog's weight at 5 and 9 years of age, and comment on the validity of this model. So the equation here would be y, or w for weight. W equals 3.4 is your initial value, plus 10.9t. Okay. According to this model, what is the dog's weight after 5 years? So 3.4 plus 10.9 times 5 is going to be 57.9 pounds. Then after 10 years, 3.4 plus 10.9 times 10, the dog would weigh 112.4 pounds, according to the model. And the model is only accurate for small ages because the dog will eventually stop growing. It's also going to grow at different rates. As a puppy, it grows very quickly. Then even as it starts to become an adult, that growth rate slows down. And then, yes, once it's fully an adult, it stops growing. So this is not a good model for the dog or for people or anything like that. Children grow very quickly in the first couple years of their life. Then they hit growth spurts later on, but they have periods over which they do not grow very much. So usually not good to look at linear functions for growth models. A group of climbers begin climbing at an elevation of 6,500 feet. So that is right here, where each tick mark is 500 feet here, and ascend at a steady rate of 500 vertical feet per hour. So 500 feet per hour is going to give us rise 1 tick mark every hour. This should be, and really should have a straight edge here to help me, but hopefully you all can draw that better than I can without a straight edge. And there's my linear function there for that models their climb. The situation can be modeled by a linear function. Identify the independent and dependent variables. So the independent variable will be the number of hours, and the dependent variable will be elevation. Number of hours is the independent variable. Elevation is the dependent variable. You can see that already with the way we set up our graph there. Using this, use the graphing tool to graph the line, and the elevation after 2 hours is going to be 7,500 feet. Linear model is reasonable here, as long as we stop after at a reasonable amount of time. So, because they're not going to be hiking, climbing for but so long, right? They'll have to stop after a little bit. So don't extrapolate this out too far. All right, that's it for this video, and we will come back next time and finish up talking about Unit 9B. See you for the next video.